So, in this class we will now continue with 2D NMR principles, how the 2D NMR data is recorded, and we will start to now look at a few 2D spectroscopy experiments specifically. So, let us start again with the basics of the principles of 2D, how it is acquired is shown here. So, we saw this is a very simple schematic scheme which has basically a RF pulse applied and then you evolve, and during this period we said we can transfer the polarization or magnetization to B and then it gets detected. So, again remember we saw that this is a non-selective in nature, meaning this is not just applied to one spin in particular, it is applied to all the spins in the molecule. Similarly, this is applied to all the spins. So, because of both the spin on both sides, we saw that there are 4 combinations. One is called two are called diagonal peaks, and we saw 2 will be the cross peaks, that is off diagonal. Now, let us go to the more detail of how experiments are actually recorded. So, what happens is this is called a preparation period, and this is just the period before the pulse. So, this is similar to, this is same as the relaxation delay. So, if you recall when we said for 1D NMR that when you put a sample in a system in a magnet, you have to wait for some time, because during that period the equilibrium magnetization along z axis has to be built. The building process takes some time, that is T1 relaxation, and you wait about 4 to 5 times T1. So, that is called a preparation period. You are preparing the system for applying a pulse. Then you apply the pulse, that is excitation. Then you have evolution, meaning the chemical shifts are now evolving or the oscillation is taking place in the x and y plane, and during this process it is also relaxing back to z axis and also it is dephasing in the x y axis. So, relaxation basically is happening during this time. Also the most very important thing which is going on is the transfer or the coupling of the chemical shift, one chemical shift whichever is excited here to another spin to which it is interacting by J coupling. Now, after this period we now apply a second pulse which is again non-selective in nature, it is applicable to all the spins, but now this brings into xy plane only those spins which are along z. So, that means when during this transfer of magnetization it has transferred from A to B, but the B when it is transferred, the B is not along xy, it has been along z. So, the transferred part is along z, but the non-transferred part is along x. So, this transferred part which is along z has to be brought into the xy plane by applying a second pulse. So, this is called a mixing pulse. Why is it called a mixing? Because we are mixing the magnetization from A to B, because the transfer took place here, but transfer does not mean it can be detected, because after transferring the second spin is still along z axis. So, that has to be brought into xy axis plane by applying a pulse, and that is called mixing pulse, and then after that we start detecting the spin evolution of the second nucleus which has now been excited, and that is a physical detection, that is called the FID, means signal is inducing a current or EMF in the coil similar to what we saw in 1D. So, this is actually like a 1D FID. So, this scheme is shown again in this picture. So, we have a preparation period which before applying the pulse, we apply the pulse, we have an evolution period, and then we have a mixing pulse, and then it is an evolution again because the second spin. So, this process is repeated n number of times. So, this is the preparation period which is relaxation delay. So, now we are applying RF pulses. So, this process is repeated a number of times. So, that is called a scan. So, one scan means one single whole process which goes from relaxation delay to the end of the acquisition. Acquisition means end of this. Then you again go back to this period when during the relaxation wait for the complete relaxation delay, then start applying a pulse. So, this like that you can keep on doing this n number of times, and that is how we call the number of scans. So, this is basically called signal averaging, because we are trying to get rid of the noise by averaging out the noise. So, signal is enhanced. So, signal to noise is increased. So, this is basically the schematic. Now we will start moving into more specific experiment. So, in this course we are not going to cover the entire 2D NMR gamut of experiments, because that will basically take a very large amount of time. So, I would only focus on a few key important experiments 2D NMR, which is typically used by 90% of the chemists who use it in their organic chemistry for organic molecules. Also it is the experiments which are used by peptide chemists, because peptides also we do work with homonuclear NMR. So, this is called as a homonuclear NMR experiment. Homonuclear meaning, remember, is proton to proton correlation or carbon to carbon correlation, both are the same nucleus. So, we use the word homonuclear. Then we will look at the heteronuclear, meaning we are now using carbon and proton together, and in one axis will be carbon, another axis will be hydrogen, or you can use carbon and nitrogen or any combination of heteronucleus. But 90% of the experiments are typically proton to carbon, but proton to nitrogen is also very popular in the case of analyzing when we analyze biomolecules. So, we will look at specifically these 3 experiments only 2D NMR, and this basically illustrates a lot of principles of 2D NMR. And when we do the application part, this will also all this will be useful, because as I said, mainly these are the set of experiments used by a maximum number of people for their research analysis. So, now if you look at the names, NMR is full of jargons or full of names, acronyms. So, that is these acronyms one should know from where they come. So, that is what is shown here. So, COSY is the most famous 2D NMR experiment. In fact, one of the first experiments which was published, and the 2D NMR started its beginning from there, that is by Richard Hunt, but the ideas were already known before Richard Hunt published. So, the idea of COSY, with the word COSY comes from this correlation spectroscopy. TOCSY comes from total correlation spectroscopy. So, we will see this as we go along. So, you can see there are many interesting acronyms, and these have become basically the jargon in NMR. And similarly here use the word HSQC, which says heteronuclear single quantum correlation. So, the words, each one of them sounds very technical. So, we will not go into details of why this, what is quantum, single quantum and so on, because the Tech 4 course is more on focused on the basic aspects, but we will see now, we will see later on how these experiments are useful. So, let us start from the first experiment, which is correlated spectroscopy, or you can say correlation spectroscopy. So, remember in NMR every experiment has an associated with it a pulse sequence. So, we defined that pulse sequence earlier. Pulse sequence is basically the blueprint of how an NMR experiment works. Okay. So, for example, if what is a pulse sequence for a 1D, it is nothing but a simple one pulse. But what is a pulse sequence for a 2D? It will have not just one pulse, it will have a pulse, it will have some delay which is called evolution, then it will have another pulse which is called mixing, and then acquisition. So, you see there are series of pulses applied and a delays in between. So, we use the word pulse sequence for the complete sequence. So, now let us look at this homonuclear COSY experiment. So, this is how it works. So, you have a 90-degree pulse. So, now we will start using little bit more technical terms. So, this pulse which I earlier labeled it as RF pulse is basically a 90-degree pulse, means RF flip angle. The flip angle is 90-degree and it is applied along the x axis. So, what basically it means that magnetization which is from z axis before this pulse is flipped by 90 degrees and it comes to the xy plane, and then during this period it evolves. So, this is what we already saw. So, this in fact is already the scheme for COSY. So, although we did not use the word COSY earlier, but what was happening, the illustration what was being shown for the general 2D scheme is actually was taken from this scheme for COSY. Then you apply the second pulse which is an mixing pulse, and remember during this period there are 3 things going on. Number 1, it is a chemical shift evolution oscillation in the xy plane. Number 2, relaxation to the z axis as well as in the xy plane, and number 3, transfer of magnetization to the second spin, a neighboring spin. Okay. So, this is simplest of all experiments in 2D, nothing can be simpler than this, and this is in fact the one of the first ideas how 2D was proposed. So, let us see now in a vector diagram what is going on. So, in NMR it is very useful to analyze this kind of pulse sequences with this kind of a vector diagram, because this gives you a more clear picture of what is going on with these vectors with the magnetization. Remember, this is the equilibrium magnetization, and that is all we have to start with the experiment. We have to come back to this position again to start the next experiment, next meaning next scan. So, every scan, again remember in the previous slide we saw every scan you have to come back to equilibrium, and for that you have to wait for 3 to 5 times the relaxation delay, 3 to 5 times the T1 relaxation, and that is called relaxation delay, and that period is about few seconds or it can be few tens of seconds depending on the T1 value. So, therefore, we will start from here, which is already assuming that it has come to equilibrium. Then I apply a pulse. So, when I apply a pulse, the magnetization has come by 90 degrees from z axis, and this is what is basically because of this RF pulse. And remember, I am ignoring this where it is along x or y, I will simply use the word xy, means it is in the horizontal xy plane. But technically speaking, this is not really the correct way to say, but for understanding purpose we can say generally that whatever be the pulse here, whether it is x or y, we still will use the word that it is in the xy axis plane. So, now when it has come to the x axis, let us say the cosine omega t is the evolution part, that is how it is FID is evolving, chemical shift is evolving during T1. So, that is shown by this arrow black color here, that it is simply turning around. So, this is the oscillation which is going on in the xy plane because of this chemical shift omega A. But remember, there is also what is happening is the dephasing in the xy plane, and that is not shown here, and dephasing is basically the T2 relaxation. So, that part I am not going to show here. All now I am going to talk about is how these frequencies are basically happening. So, this is how it is happening in the xy plane. Now, you transfer to second spin B, and the second spin B now gets excited, and that is shown with this black arrow, bluish arrow. Now, this bluish arrow is basically now the spin B, and that is now evolving in the time. So, this is again a repetition sort of the general 2D schematic. Now, let us go and see what kind of spectrum we get. So, now what is the conditions for a 2D COSY to happen? The 2D COSY to happen, the condition is that they should be coupled by J coupling. This is the most important thing, that they should be directly coupled, two protons. If they are directly coupled together through J coupling, then only you can expect to see any cross peak or peak between those two atoms. So, as we saw in the schematic picture, that the diagonal peak corresponds to the 1D spectrum. Let us see this in the next slide. This is what is shown here. So, if you look at it, these are nothing but the same frequencies appearing both on this axis and as well as this axis. So, there is nothing but a simple 1D information. Suppose I had recorded a 1D of this molecule, I would have got two peaks at A and B, right. So, hydrogen atom, two hydrogen atoms at A and B protons. So, I would have got two peaks. Okay. Of course, there would have been a J coupling. So, this would be a doublet, this would have been a doublet. So, in a 2D also, although we are not showing here, there is a doublet hidden here, there is a doublet here, there will be a doublet here in both the dimension. So, remember in NMR the coupling will appear in 2D NMR, the coupling will appear in both axes. Why? Because if you go back to this picture, this is also like a 1D and this is also like a 1D. Therefore, if there is a coupling here splitting because of J coupling, the J coupling splitting comes here also. Of course, this is the 1D standard 1D spectrum, but this is also like a 1D. So, therefore, in a 2D, although we do not show like this, I am showing only like a circle here, because I am trying to explain qualitatively, but in reality you will actually get two peaks doublet here also for A if it is coupled to B, and similarly in this side this B also will show two coupling doublet to A. Similarly, in this dimension, the horizontal, here also it will have a doublet and here also it will have a doublet. So, what will be the case? Let us see this pictorially now. Let me explain. So, if you see, you have basically a doublet in the T1 part. Let us say we are looking at A, and here also we will have a doublet. again let us say we are looking at A. So, what you will get is this to this will give you one peak, this to this will give another peak, this is another peak, this is another peak. So, you will see 2 into 2, 4 peaks. So, basically this whole thing is actually like this. Okay. So, inside this peak red color A, you are basically having 2. Similarly, if you see here, if you zoom this, here also you will get 4 peaks because of J coupling on this side and J coupling on this side. Okay. So, what you are basically getting inside this blue peak is of B is basically 4 smaller peaks. So, that is what is there. So, but of course, we will not consider those smaller multiplets inside the peak, because for as far as this 2D is concerned, remember why are we doing 2D NMR? We are doing 2D NMR not for measuring the couplings. We are using 2D NMR for using the couplings to transfer the energy magnetization from A to B. So, our interest goal is not to measure J coupling. So, for if you want to measure J coupling, you can always do it from a 1D NMR, but our goal is to correlate two frequencies. So, when we correlate, we only then look at the center of the peak. So, our focus will be at the center. So, this whole thing will be now our center is actual value chemical shift, because remember the chemical shift of A is not this or this, it is at the center. Similarly, the chemical shift of A is again here the center. So, our center of this peak is our actual chemical shift value, and that is what we are interested in and not in the coupling. Okay. So, now similarly cross peak will also have a multiplet structure inside this, but as far as the analysis is concerned, we normally do not consider that, we only focus on the overall position, means the value of the chemical shift here in the center. Okay. So, you see this is marked as X because it is a cross peak. So, cross is X. So, we use the word cross peak. Sometimes in literature or in textbooks, people we also use the word off diagonal. This is diagonal and this is off diagonal. So, keep this in mind. Third nomenclature which is used in literature is called transpose peak. So, if this is a peak, the transpose of this peak is here. Similarly, the transpose of this peak is here, similar to what we use in the matrix algebra nomenclature. So, these are the different terminologies which you will come across in the books as well as when I am talking about this. So, this is a diagonal peak and this is the cross peak. So, now let us just again look at a schematic for a molecule. So, I am not going to show you the actual spectrum here, but schematically what you expect to get if you record a 2D COSY on let us say this molecule. Okay. So, we have propyl chloride. So, this 1 here has got displaced. So, this is 1, this is 2. Okay. So, we are 1 is this, 2 is this and 3 is this. So, we are again remember we are looking only at the protons, hydrogen, we are not focusing on carbon. So, when you record a spectrum of this 1D NMR, this you will get something like this. Why is 1 is here? Because it is downfield shifted, again remember because of the inductive effect. Then 2 is little bit away and 3 is the last, because 3 is most away from carbon as chlorine. So, therefore, it is least de-shielded. So, it comes here. So, this is fine. Now, let us ignore the J multiplet pattern. So, remember again when we go to 2D NMR in this entire course, we will not be focusing on the J multiplet in 2D. Okay. So, J multiplet as far as 1D is concerned, we have already looked at it and saw how we can use it for getting the structures, but when it comes to 2D we normally consider them. So, now let us come to the 2D here. So, I get a 2-dimensional plane. So, this is a 2D NMR. So, I am recording 2D of this spectrum. So, you will have a one axis which is T1 axis, that is all proton, and this is also proton. So, we are looking at 2D COSY, which is a homonuclear correlation experiment. So, that means both dimensions will be hydrogens, protons, or both can be carbon. So, we can also have a carbon COSY, keep in mind, and we can also have a proton COSY, but again the most popular is proton COSY, and we are going to look at only proton-proton correlation. So, now if you look at this molecule again, so which is coupled to which? Now we see 3, if you look at this 3 hydrogen number 3 methyl is J coupled to number 2, 2 is coupled to 1 and 2 is also coupled to 3, because remember if one atom is coupled to another atom, the other atom has to be coupled again to the previous one. So, if atom A is coupled to atom B by J coupling, atom B automatically is coupled to atom A by J coupling, both are coupled to each other. So, 2 is also coupled to 3 and 2 is also coupled to 1. Similarly, if you go to 1, 1 is coupled to 2. So, now what do we expect to see in this kind of a spectrum? What we expect is a correlation, means connection between two hydrogens which are coupled to each other. So, that means I expect on this axis a correlation. If you look vertically, if this is 3, that means let us start from here. If this is 3, I expect a correlation from 3 to only 2, and I expect a correlation from 2 to both 1 and 3, and in 1 in this line I would expect to see a correlation from 1 to 2, but I would not expect to see a 1 to 3 connection. Why? Because 1 to 3 are not connected or coupled to each other. So, obviously, I do not expect any correlation in chemical shift between 1 and 3, okay, because when magnetization of 1 evolves, it cannot transfer to both 2 and 3 because it is not coupled to 3. So, now let us see what happens in the peak pattern. So, this is first thing is diagonal peak. Remember, every 2D homonuclear experiment is it always has a diagonal peak. Why is that? You have to recollect a few slides back, we said in the last class the transfer efficiency cannot be 100% in homonuclear, it is always less than 100%. That means part of the magnetization is retained on its own. That means if I have spin A and B or 1 and 2 in this case, the one magnetization proton 1 will not transfer all its energy of magnetization to 2, it will keep almost a lot of it on itself, 80% typically. So, only 20 to 10% will go this side. So, that means that one which does not go anywhere, which is 80%, will evolve at during T1, that is during vertical axis, in omega 1, that is chemical shift of 1 and it will also evolve with chemical shift of 1 in this axis, because it has not transferred 80% of it. So, therefore, a Fourier transform there gives you a diagonal peak, which is on both axes, it is the same chemical shift. So, you can look at this picture here, both of them in this axis as well as this axis has the same value. So, we call it as a diagonal. Similarly, if you look at this peak here 2 and 2, there will be always some peak here and 3 and 3. Again keep in mind we are ignoring the J coupling pattern inside the peak. So, this peak is actually not like a circle, it will be like a 4 peaks inside this, but we are going to ignore because our focus is on the chemical shift value, which is the center of this, Okay. So, this is diagonal peak. So, what is the use of diagonal peak? Basically, it is sort of useless, it has no value for us, because what does it give? It does not give any information, it only says this is this and this is this on both axes. That means what extra information do I get? I do not get any information. So, diagonal peaks in NMR are kind of a trouble to us more than giving us any information. So, another one of the areas of research in NMR is to have a diagonal less homonuclear experiment. So, there have been lot of papers published where scientists have tried to get rid of this diagonal, but remember it is not very easy, because this is something which behaves like its magnetization. You cannot distinguish in NMR between what remains on itself and what is transferred to somebody else, both of them look the same. So, how do I selectively suppress or remove the diagonal, but I want to keep the transfer information, okay. So, that is called cross peak. So, we will see now the cross peak. So, first let us see between 1 and 2. So, as expected between 1 and 2 I would get a cross peak. That means, if you draw a line like this from here to here and here to here. So, these two green atoms are 1 and 2, and common to 1 and 2 there is a connection, there is a correlation between 1 and 2 which is reflected or shown in this red spot here. So, this peak, the presence of this peak itself tells you that these two atoms are correlated, means connected. Okay. So, that is a very useful information you are getting here now. In a 1D NMR, I would get simply 1, 2 and 3. I would not get the information whether the coupling what I see here is because of 1 to 2 coupling or is it because of 1, 2, 3? If I have structure in my hand, yes, then I can say that it is 1 to 2, but if I do not have a structure and my goal is to get a structure, if I do not have information of this and I have only this spectra 1D, definitely it is very difficult to say was 1 is coupled to 2 or 1 is coupled to 3. Only if I do this 2D NMR COSY experiment, then I immediately get the information that these two atoms are connected to each other. So, in case I am getting a doublet here, which is not shown, but in case you are getting a doublet here, the doublet is only because of its coupling to 2 and not to 3. So, that is the take home or important message we should see from this analysis. Similarly, if you look at this side, this is nothing but a transpose, means a mirror image, a reflection, because remember both ways the transfer takes place, it goes, energy goes from 1 to 2 as well as 2 to 1. So, we saw that in the previous slides and previous class. So, I expect a mirror image symmetry. So, this is an extra peak. Our interest is only on this one or this one, we do not need both, but it is sometimes good to have, so that we can confirm that this is really a correct peak. Now, let us move on to the second pair, which you see here between 2 and 3. I expect coupling between this 2 hydrogen and this 3, and that is also is shown here. So, this again confirms that if I, so what will be the peak pattern of 2? It will be a quintet. Why it will be a quintet? Because there are 2 protons, sorry, in fact it will be a sextet. Why it will be a sextet? Because there are 3 protons on one side, 2 on this side. So, the proton 2 you will get actually 6 peaks, but then that 6 peaks does not tell me to what it is coupled. Of course, in the case of this it is easy to say it has to be coupled to this side and this side, but if I have number of peaks, the sextet does not tell me any information to actually which other 2 hydrogens it is coupled, and that information coming from here. So, this says that 2 is coupled to 3 and also 2 is coupled to 1. So, this 2 is actually now 2 is also coupled to 1. So, this 2 is basically what is shown here, 2 is coupled to 1 and 1 is coupled to 2, and this 2 is also coupled to 3 and 2 is coupled to 3. But if you see these 2 peaks, there is no peaks here. Why? Because 1 is not coupled to 3. Okay. So, this line arrow which I am showing now is a indication of between coupling between 1 and 3, but there is no coupling. We do not expect any direct coupling from 1 to 3. So, in a COSY you will not get any cross peak between 1 and 3 for this molecule. Similarly, from here you will not get 3 to 1 connection. So, this portion will be empty. So, only peaks you will get is this red color cross peaks, the green color diagonal peaks and the blue color cross peaks. Okay. So, this is how basically it helps you to figure out what are the coupling patterns in a molecule by simply recording the experiment 2D homonuclear COSY, which is one of the simplest experiment. We will see a real spectrum in the next class, where we will look at a real molecule, where we will see a real molecular spectrum and see how interactions are revealed between 2 protons, and the interaction between 2 protons are revealed in a 2D COSY experiment. But remember again, 2D COSY experiment is only giving you connection between 2 protons which are directly coupled to each other. Okay. So, in the last example we saw it is not giving any cross peak between the protons 1 and 3, but there are interesting experiments which can also give 1 to 3 connection even though they are not directly coupled, and that is a very famous experiment called 2D TOCSY. So, in the next class we will go to 2D TOCSY along with some more examples of COSY.